Hello, my name is David. This is Group 5, and our project is on tobacco and cancer. First is smoking and cancer and the evidence. So these two gentlemen on the right are Richard Dahl and Austin Bradford Hall. So in the 1950s, these guys came together and found the link to smoking and lung cancer. So with this discovery, it led to a lot more findings down the line and overall reshaped the public health view around smoking and cancer. And after that, that leads us to the current day stats. Between 85% and 90% of lung cancers are attributable to smoking. So basically, if you're smoking cigarettes, doing all that, there's a good chance you're going to get lung cancer. Uh, Now, in today's age, there's over 8 million tobacco related deaths per year. So, this is a very shocking number, a lot more than I thought originally. It just goes to show how many people do smoke on a daily basis and how deadly it is. Smokers have a 20 to 30 times chance higher of lung cancer risk. So, me, a person who doesn't smoke, uh, a person's chances of getting cancer compared to me is going to be 20 to 30 times higher than against someone who smokes. So it just goes to show how much of an accelerant it is. Other cancers linked to the tobacco include oral cancer, larynx cancer, esophagus cancer, bladder, pancreas, kidney, cervix, stomach, and so on and so forth. Next, I will be talking about tobacco smoke chemistry beyond nicotine. Tobacco smoke is a very complex and complicated assortment of chemicals that combine to make a overall deadly mix. Uh, Over 7,000 chemicals are in the contents of tobacco smoke, which is a very shocking number. Um, just just thinking about all those chemicals in one compound, uh, surely is just very scary and daunting. Over 70 known human carcinogens are also in tobacco smoke. So, carcinogens, for people who don't know, are chemicals that attribute to cancer growth. So, over 70 of them just in tobacco alone is very scary. It shows how really like the potency of tobacco smoke is, and it's just crazy. Also, as well, with the addition of nicotine, which causes addiction, which in my opinion is probably the most dangerous chemical of them all, just due to the fact that it rewrites your brain, makes you crave and need cigarettes just to function. So that just it pulls you in that abyss, and you just keep going and going and going, and then eventually you get sick beyond any way to come back. Major classes of carcinogens. So for the classes, we have PAHs, polyenic aromatic hydrocarbons, TSNAs, tobacco-specific nitroamines, aromatic amines, volatile organic compounds, heavy metals, and radioactive elements. So for PAHs, we have benzoaprine or BAP, and the primary effect of that is DNA abduct formation, which is like just will mess up the DNA and lead to all sorts of bad stuff and like mutations. Next for TSNAs, we have NNK and NNN, which leads to DNA mutations like tumors, basically, just rampant cell growth, really, really bad. For aromatic enemies, we have 4 amino by phenyl, phenyl, which will lead to bladder cancer. Next, we have volatile organic compounds, which for those is benzene and formaldehyde, which can lead to oxidative stress and DNA damage. Next, we have heavy metals. We have cadmium and arsenic, which can lead to genotoxicity. And lastly, for radioactive elements, we have polonium-210, which can lead to DNA damage. Next, we have key carcinogens, BAP and NNK. For BAP, a polycyclic aromatic hydrocarbon or PAH, like before, forms during tobacco combustion. And tobacco combustion is just the lighting up of a cigarette. So think of that. As soon as you light up, you light up. It leads to an explosion of deadly chemicals that gets inhaled by your body and damages your DNA and other things. Then it is activated by cyclone P450 enzymes into PPDE, a highly reactive compound. Lastly, it is often linked with TP53 gene mutations. Uh, for NNK, we have a tobacco-specific nitrosamine found in exclusively in tobacco products. So this you'll mainly find it in cigarettes and such things that contain tobacco, not really anywhere else. It is activated by citrone P4050 enzymes, just like BAP. And lastly, this is strongly associated with KRAS mutations, um, lung adenocarcinoma, and pancreatic cancer. And on the right, you see the makeup of BAP and NNK.
Hi, my name is Gabriel, and I'm going to go over this following section of the presentation. And we're going to go through now metabolic activation versus detoxification of tobacco carcinogens. Many people, like the vast majority of the population, thinks that and tobacco smoke themselves have carcinogens, but this is not true. They have chemicals that are inactive procarcinogens. These by themselves do not cause any DNA damage or disrupt any processes. But when these chemicals are metabolized by the body inside the cells, they become carcinogens. And the body has its own pathways, its own ways to detoxify these compounds. It has two phases, but it can also produce harmful metabolites. Like we're going to go through the case of BAP, which is benzoate-pyrene. In the phase one of this detoxification, cytochrome P450 family of enzymes like CYP1A1 or CYP1B1 or CYP2A6, they add oxygen to BAP, and also make compounds more water soluble. Unfortunately, this can convert harmless compounds into carcinogens, turning them into reactive electrophiles. So this is the phase, the part where the bad stuff happens, where the non-carcinogens, so the pro-carcinogens, which are not carcinogens yet, turn into carcinogens. Then in phase two, GST or glutathione transferases or UGT, UDP glucuronyl transferases, they attach molecules like glutathione or glucuronic acid to carcinogens and make it more water soluble as well, but this time to be removed as urine. So we can see that there's two paths it can go. BAP can go through phase one, and which it converts into a reactive metabolite, and then it can go to DNA to bind DNA and affect it and cause a mutation, or it could go straight to phase two and get detoxified and excreted. It is truly a balance of like a fight in these two paths it can take. If more metabolic activation happens, more DNA binding and more mutations and more, there will be more risk of cancer. But if more detoxification happens, then it will be the contrary. Cancer will occur and the body would effectively get rid of these compounds, which are very bad for cancer risk. Formation of the ultimate carcinogen, BPDE. Um, for understanding this process, we have to know that there's modulator, like a switch or a sensor in the cell called AHR. AHR detects um, the amount of harmful or possible harmful chemicals like BAP, and it upregulates the the formation of the cytochrome P450 family of enzymes, like for example, let's say CYP1A1 or CYP1B1. When BAP or BAP gets metabolized by these enzymes, it forms a BAP trans 7,8 dihydrodyl intermediate and then forms an anti-BAP78 diol 910 epoxide, which is the famous BPDE, or the sometimes referred as the ultimate carcinogen. It is very, very dangerous because it has an epoxide ring, and epoxide rings are highly unstable and reactive. They, as we will see later, they bind to the N2 side of guanine, which is a nucleotide base pair, a base, and it will, as we'll see later, disrupt DNA transcription, for example. But yes, this epoxide ring will bind to guanine in the N2 position and will, by some concepts we will see later, cause a gene mutation. So the DNA adduct formation by BPDE. A DNA adduct is the chemical, like this in this case, BPDE covalently attached to DNA, mostly in the case of guanine. This makes that the DNA becomes inaccurate. The mechanism for this is that, as I said before, BPDE binds to mostly to guanine. It forms the BPDE DNA adduct. And when DNA polymerase encounters damaged DNA, or for example, a guanine that it wasn't supposed to be binding to BPDE, an incorrect base is inserted, and this causes a mutation. The biological consequences of this is that DNA adducts distort DNA, which means what I said before, the right base pair is not going to be added. It blocks replication, interferes with transcription, and increases the mutation rate. The clinical importance in this scenario is that smoking-associated cancers often contain GT transversions, especially in the TP53 gene, which is key for tumor suppressor P53 gene, which will suppress the tumors in together with other processes in the body. But if this process is damaged, in this gene that suppresses tumors is damaged, then cancer will be more likely to occur. And as I said before, it binds to the N2 position of guanine, and it could be on the trans or cis conformation. Both are harmful, and yeah, the big deal here is that this epoxide ring will react with DNA. It's very unstable. Then oxidative stress and reactive oxygen species. Um, yes, so reactive oxygen species are very harmful for the body because they, for example, oxidize guanine, producing 8-oxo-DG or 8-oxo-deoxyguanosine. These reactive oxygen species can be, for example, superoxides or hydroxyl radicals, or even hydrogen peroxide, which are contained in the cigarette and the cigarette smoke. Um, this is very important because in the clinical significance, if we see it, smoking every day, multiple cigarettes or multiple packets a day, throughout the whole day, it will create persistent oxidative stress, which will lead to genomic stability and to tumor initiation, which will also lead to tumor progression. It's a pathway that it's being reinforced by us people smoking every day. 8-oxo DG, the compound oxidized that is was oxidized. So one was oxidized and it created 8-oxo DG. It misfires with adenine. So instead of doing the DNA replication pairing G with C, it produces T with A, thymine with adenine, resulting in a mutation, which can cause um, horrible effects on the body and its processes. This ROS or reactive oxygen species will also attack proteins and lipids, not only DNA. And the body has two DNA repair pathways, NER and BER, or NER and BER. So the body has this pathways, and NER or nucleotide excision repair repairs bulky helix distorting DNA lesions, and is the main pathway responsible for the adducts that we spoke before, the BPDE adducts with DNA. It does it by detecting the DNA damage, unwinding the DNA around the lesion, and then cutting out or excising the damage of this DNA fragment, and DNA polymerase will synthesize a new DNA segment, which is new and will be free of any errors or any of these BPD adducts. And the DNA ligase will seal or glue the remaining nick. It is important because it prevents mutations caused by bulky carcinogen DNA adducts and maintains genome stability. Failure of this pathway could increase cancer risk because of the BPDE adduct, for example. The base excision pair or BER, it repairs small, non-bulky DNA lesions. So the NER repairs bulky lesions, the BER repairs small DNA lesions, primarily removing oxidative damage, slower, smaller level, smaller area, like in a compound rather than in a whole DNA strand, which is a bunch of multiple molecules intertwined together. The BER removes oxidative damage such as 8-oxo DG. That is what happens when one gets oxidized. It does it by OGG1 recognizing and removing the damaged base, and an AP endonuclease coating the DNA backbone at the empty site. DNA polymerase inserts the correct nucleotide, and DNA ligase seals the DNA strand. It is important because it prevents oxidative stress and maintains DNA integrity after a reactive oxygen species damage. And failure of BER allows oxidative mutations to accumulate. Not only failure of this pathway, but we could have this pathway working perfectly okay. But if we are smoking every day and adding oxidative damage to our body, it will outweigh the benefits of BER. So DNA damage, if it accumulates, it will lead to permanent mutations, to oncogene activation, then to tumor suppressor loss, and then what cancer will develop.
Hi, my name is Andrea. We spent the last few slides watching tobacco chemicals turn into a reactive compound. Now let's get specific about where exactly they hit. First up, it would be TP53, which is honestly one of the most important genes in your whole genome, which comes to stopping cancer. Its job is to look for damaged cells and making sure they never get the chance to copy themselves. The protein it makes is P53, which scans cells for DNA damage. it pauses the cell cycle and it gives the cell time to repair. However, BPDE is one of the carcinogens in tobacco smoke that doesn't damage TP53 randomly. It goes after the exact same 3 spots every time, which would be codons 157, 248, and 273. These mutations follow a very specific pattern called a G2T transversion, where guanine gets swapped out for thymine. That pattern is basically tobacco's like fingerprint, which it shows up almost exclusively in smokers, which means when scientists spot it, they can say it like, oh, it was caused by smoking, like automatically, because it's just an ongoing pattern that always shows up. Now let's flip over to the KRAS, which works nothing like TP53. Think of it as like a switch sitting between the outside of the cell, and it's like a control center, which basically tells it either to grow, divide, or just keep going. Normally, it's only for a split second. It flipped from an inactive GDP bound state to a brief active GP bound state, which fires a signal, and then a group of helper protein called GAPs, they come in and they flip it like back off pretty much. On the left side, you can see the normal KRAS cycle. GAP protein quickly convert GTP back to GDP, shutting the signal off, and it's delivered. That keeps the cell growing in a controlled manner. However, tobacco smoke carries a chemical called NNK, and it causes one specific mutation at codon 12 of KRAS. That one change is enough to stop GAP protein from ever turning the switch off again. So KRAS gets stuck, which permanently locks it active, and GTP bound state blasting out growth signal nonstop. So basically means that the cell just keeps growing, like the cancer cell just keeps growing if it's just in that state. Unlike TP53, which contributes to cancer by losing its function, KRAS promotes cancer by gaining a permanently active function, which is why it's considered an oncogene. Now to epigenetic silencing. Not all tobacco-related changes involve DNA mutations. Tobacco smoke also causes epigenetic changes which alter gene expression without changing the DNA sequence. One of the most common epigenetic changes would be the DNA hypermethylation. Tobacco smoke increases the activity of enzymes called the DNA methyltransferases, or the DNMTS. These enzymes add methyl groups to DNA when the promoter of the P16 gene, which is basically the on switch, the gene becomes silenced. The P16 protein is another tumor suppressor. It normally inhibits CDK4 and CDK6 and stops the cell from moving from the G1 phase to the S phase of the cell cycle and prevents damaged cells from dividing. This is very important because unlike genetic mutations, epigenetic silencing is potentially reversible. Researchers are studying DNMT inhibitors as possible cancer therapies. In tobacco-associated lung cancer, P16 often occurs early, allowing abnormal cells to keep multiplying before additional mutations accumulate or they even show up. So now let's put it all together. How does tobacco actually turn a healthy lung cell into cancer? It starts with completely normal bronchial cells getting hit again and again by tobacco carcinogens. At this point, the cell repair systems are still doing their job normally. After the irritation keeps going and they keep getting hit, the cells start multiplying more than they should. This is also right around when the P16 promoter starts getting hypermethylated. As the damage keeps piling up, the tissues move into that dysplasia. Now TP53 is picking up those 2T mutations at codon 157, 248, and 273, how I had said before, and KRAS is starting to activate too, both throwing normal cell growth off balance. Next comes the carcinoma in situ, where KRAS activation and continues P16 is silenced, which knocks off the cell remaining checkpoints, letting abnormal cells build up without getting checked by the other. And finally, once enough genetic and epigenetic damage has piled up, you get the invasive carcinoma, which means that the cancer can grow uncontrollably, build its own blood supply, dodge the immune system, invade other tissues around it, and eventually spread to other parts of the body. So the big picture is basically like lung cancer isn't caused by one bad break. It slowly builds up, repeating tobacco exposure, racking up mutations and epigenetic changes over time until a normal cell finally crosses the line and it turns into invasive cancer.
Hi, I'm Bruna, and it's important to understand that nicotine does not directly harm DNA. Instead, has gene to attach to A7 nicotinic acetylcholine receptors, or A7 and AChRs, which are present on non-neuronal cells, such as lung cancer cells and normal lung epithelial cells. The ion channels of these receptors is open when nicotine binds to them, allowing calcium ions to enter the cell. Numerous intracellular signaling pathways are triggered by this rise in calcium. Consequently, these pathways stimulate cell migration, which makes it easier for the cells to spread. Increased cell proliferation, which means that the cancer cells proliferate more quickly, and it improves the cell survival by assisting them in avoiding programmed cell death, and it speeds up cancer growth. The important thing to keep in mind is that since nicotine does not directly induce DNA mutations that causes cancer, it is not considered a tumor initiator. It stimulates the growth, the survival, and the aggressiveness of already existing cancer cells, so it functions as a tumor promoter. Nicotine activates multiple intracellular signaling pathways after binding to the A7 nicotinic acetylcholine receptor. The PI3K/AKT and the MAPK/ERK pathways are two of the most significant ones. The PI3K/AKT pathway mostly aids in the survival of cancer cells. It stops apoptosis, which is the programmed cell death process that typically eliminates damaged or abnormal cells. Additionally, it inhibits BED, a protein that encourages apoptosis while increasing BCL2, a protein that keeps the cell from dying. Because of this, cancer cells are able to survive longer than they would. The MAPK/ERK pathway simultaneously promotes DNA synthesis and boosts cell division. This causes the cancer cells to proliferate more quickly, which speeds up the growth of the tumor. By enabling aberrant cells to proliferate and survive longer, these pathways work together to generate an environment that promotes the development of cancer. Because it doesn't directly cause DNA alterations, nicotine is regarded as the tumor promoter because it triggers signaling pathways that aid the survival of already existing cancer cells. These cancer cells eventually need more oxygen and nutrients in order to survive and multiply. The tumor becomes bigger and eventually needs its own blood supply as cancer cells keep multiplying and survive. Tumors cannot grow in the absence of nutrients and oxygen. Vascular endothelial growth factor, or VEGF, is a signaling molecule that promotes angiogenesis, which is the creation of new blood vessels, and is stimulated by tobacco smoke. As demonstrated in the picture, these new blood vessels develop inside the tumor and supply nutrition and oxygen to sustain the tumor's growth. Additionally, they give cancer cells a chance to enter the bloodstream and spread to the other areas of the body. To put it in the aggressive next. Tobacco smoke not only encourages angiogenesis and cell survival, but also produces the tumor microenvironment, a persistent inflammatory environment surrounding the tumor. NF kappa B, also known as NFKB, is a transcription factor that is activated by tobacco smoke and is one of the main regulators of this process. When NFKB is activated, it produces more pro-inflammatory cytokinesis such as TNF alpha, IL-6, and IL-1 beta. These cytokinesis sustain persistent inflammation and communicate with surrounding immune cells and cancer cells on a constant basis. Tumor growth is encouraged by this inflammatory setting, which also modifies the tumor microenvironment in ways that promote the advancement of cancer. Additionally, matrix metalloproteinases, or MMPs, are stimulated by NFKB activation. The extracellular matrix, which typically serves as a structural barrier around tissues, is broken down by these enzymes. Degradation of this barrier makes it easier for cancer cells to infiltrate surrounding tissues, which raises the risk of metastasis. In general, persistent inflammation actively contributes to the aggressiveness and the evasiveness of tumors rather than simply accompanying their malignancy. Tumors develop strategies to evade the immune system's detection and destruction as they become more aggressive. We've seen how tobacco encourages the formation of tumors through a number of different mechanisms. Avoiding the immune system is one of their last strategy. Lung cancer cells express more programmed death ligand 1, or PDL1, on their surface when exposed to tobacco smoke. This picture shows how PDL1 attaches to the PD-1 receptor on cytotoxic T cells. These T cells identify and eliminate aberrant cells under normal circumstances, but when PDL1 binds to PD-1, it delivers an inhibitory signal that reduces T cell activity, exhausting the T cell and making it incapable of attacking the tumor. Because of this, cancer cells are able to avoid immune surveillance and multiply without being destroyed by the body's immune system. This discovery led to the development of immune checkpoint inhibitors, including anti-PD-1 and anti-PD-L1 treatments. These medications prevent PD-1 and PD-L1 from interacting and enables T cells to identify and combat cancer cells once more. When taken as a whole, these molecular processes demonstrate that smoke not only damages DNA to cause cancer, but it also encourages angiogenesis, immune evasion, tumor survival, and chronic inflammation, all of which results in the development of cancer. Although both traditional and electronic cigarettes expose consumers to dangerous substances, the method used to manufacture both of them are different. Conventional cigarettes are made by burning tobacco. Thousands of chemicals are produced during this process, including important carcinogens, including carbon monoxide, tobacco-specific nitrosamines, polycyclic aromatic hydrocarbons, and numerous other harmful combustion products. E-cigarettes, on the other hand, do not burn tobacco. They produce considerably fewer carcinogens associated with combustion since there's no burning. Reactive oxygen species, or ROS, and dangerous substances like formaldehyde and acrolein are still produced when the e-liquid is heated. Although e-cigarettes have lower exposure to several carcinogens found in regular cigarettes, they're not risk-free and may still contribute to disease since the compounds can cause oxidative stress and cellular damage. A key clinical implication of tobacco-associated lung cancer is its impact on tumor mutational burden, or TMB. Over many years, tobacco smoke resulted in thousands of DNA mutations. Tumors with a high tumor mutational burden, a high number of genetic changes, develop as these mutations build up. These mutations result in abnormal proteins that are known as neoantigens, which the immune system can identify. Tumors with a high TMB are frequently simpler for immune cells to recognize because they exhibit neoantigens. But many of these tumors are also express PDL1, which inhibits T cell function and permits the tumor to evade immune response, as we saw on the previous slide. Immune checkpoint inhibitors, including anti-PD-1 treatments, can be quite successful because of this. By reactivating the T cells, these medications allow them to identify and eliminate cancer cells. Therefore, while tobacco smoke plays a role in the formation of cancer, the many mutations it produces can also make some tobacco-associated malignancies more vulnerable to immunotherapy. In conclusion, rather than pathogens in tobacco smoke damaging DNA and causing mutations that may lead to cancer, then by triggering signaling pathways that boost cancer cell survival and proliferation, nicotine encourages the growth of tumors. Tumors need VEGF to promote the growth of new blood vessels as they expand, guaranteeing a steady flow of nutrients and oxygens. Additionally, by activating NF-κB and inflammatory cytokinesis, tobacco smoke produces a chronic inflammatory environment, and matrix metalloproteinases facilitate the invasion of surrounding tissue by cancer cells. Lastly, PD-L1 mediated immune evasion allows many cancers to evade immune system destruction. It's interesting to point out that many mutations brought on by tobacco smoking can also increase a tumor's vulnerability to current immunotherapies, such as immune checkpoint inhibitors. Overall, understanding these molecular mechanisms not just explains how the tobacco contributes to lung cancer, but it also helps guide the development of targeted therapies and more effective treatments. These are our sources that we used. Thank you.